Hello everyone, and welcome to another session of Computational Algebraic Geometry. We're going to be learning more about coding in Magma. So at the end of this lecture, you should be able to write slightly more sophisticated commands in Magma, especially functions. So this is what we will focus on today. And since our focus will be on functions and not so much algebraic geometry today, your homework will also be to program Conway's Game of Life. So you can read about Conway's Game of Life. In fact, I strongly urge you to read most of this Wikipedia article. It's a lot of fun. But the rules are here, and you can simulate, instead of having an infinite grid, you can simulate the game of life in a finite grid. So you will simulate it in a matrix, and you can, for example, try to create the initial conditions so that you have these two spaceships producing gliders. Before you attempt coding Game of Life into Magma, I recommend that you take a look at the Solving Problems with Magma book. This book is freely available, and the link will be in the info box below. So there is a section on the forest fire. So this forest fire is a cellular automaton with probabilistic behavior. So it's like Conway's Game of Life, except it has a probabilistic feature, but it's simpler because it's taking place on a one-dimensional space rather than the two-dimensional space in which the Game of Life takes place. And now here is the full code for this simulation. It's very simple in that it just uses a core functionality of Magma. And in the end, you input the state of your forest as a sequence like this one. Each 1 represents a tree and a 0 represents an empty patch of ground. So there's an occasional fire and certain trees burn down. New trees can emerge from empty patches of ground and so on. So this behavior then creates changes in your forests. For example, this is the 5th state of their forest, and this is the 200th state of their forest. Now this is something which you can study here and try to implement your version. What I will do today is to talk about how functions can be defined, and we will also talk a little bit about sequences. And overall, after this, you should be able to understand the function created here, and you should be able to modify it so that you feel comfortable with your version. And finally, you can try to implement in the same spirit, with states being represented not by sequences but by matrices. You can try to simulate Game of Life. All right, let's begin. Everything I say today will work on the Magma online calculator, but now I have a local installation of Magma, and I hope you do too. Therefore, we can just go ahead and use our local version. Now, this is where I'll be typing my commands so that they will be executed by Magma. On the other hand, on another window of my terminal, I have my text editor open. So this is where I will code because there's syntax highlighting here. Let's begin by defining a function that does nothing. Okay, so this is the syntax. You start by writing function. You write the name of your function. I chose the name nothing. And then in parentheses, you list the inputs and the names of the inputs that you like to take. So this takes nothing as input. And then it returns the text here. You must end this line with a semicolon, as pretty much every line. But of course, you do not end this line with a semicolon. That's the start of a function. And you end with end function. All right, let's copy this and paste into Magma. Now we can execute the function and see what happens. It returns the string as expected. All right, after a function that does nothing, it can only go up. So let's do something a little bit more interesting. How about we construct an identity function? So I will write down ID of A. So ID was the name I chose for my function, identity. And it takes an input. It takes only one input. I will refer to this input by the letter A, and the only thing this function does is to return it. Let's copy and paste, and now we can try our function. And I can also input some text. So we've seen a function that takes nothing as input, that takes one thing as input. Let's construct one function that takes two inputs. I will call it add. And it will return the addition of the two inputs A and B. So I'm referring the two inputs as with these two letters, so I can use them inside my function. Of course, I could have called this function anything else. It could have been called potato, that's fine. So for example, potato 3, 5 returns 8. Of course, it's terrible to call your functions names that do not explain what the function does. So I will change it back to add. Now add 3, 5 is much clearer. Very good. Now we could keep going. For example, I could write A, B, C and then add these 3. Now it's clear what's going to happen. I will add these 3 things. But this is not quite fun. I don't want to write many different functions that take different numbers of inputs. That's certainly possible, not as a function, as an intrinsic, but never mind. There's a way to go around it. So let's change our add function back to its original state. I want to write a function that takes many inputs, and perhaps arbitrarily many, and then sums up those inputs. So I will call my function add all. Now I don't know what goes in here, so let's leave it blank for now. And then what we will do is to say this function is in progress as we figure out how to do it. So this xxx doesn't mean anything. So the notation is that you write 3 dots after your last named input, and that will make the number of inputs for this function flexible. But in fact, it's not quite the same notation as before, because the last of the named inputs, B in this case, will play a different role than A. A is the usual input, but B will capture all inputs after A, so after the first input. So let's see what this thing does. Now I'm using the print function. So the print function just displays what comes next. You need to use the print function when you want to see intermediate operations that are taking place inside a function. Let's copy this and see what happens. Add all, let's say 1, 2. All right, the first input is correct. It returned my first input, but it did something strange to the second one. So we can appreciate what's happening if we increase the number of inputs. So now B is 2 and 3, and I could do more, of course. So as you can see that the triple dots notation really refers to the last named input. The last named input captures all inputs as a list. So this star notation is a list. If you encounter something and you don't know quite what it is, you can try to define it yourself. And then ask, what is it? And to ask, what is it? You ask type, what is its nature? In this case, we find out that this is a list. And then you can ask, what is a list? By this time with a question mark into its help command. Well, there seems to be, I'll just take the first input. When confused with many options, just take the first one and see what happens. Oh God, there are more options. Now I need to write +1 if I need to read more. And there you go. So there is an explanation as to what is a list. It's so fundamental that you had to choose 3 options to read about it, basically. But now the key fact here is that lists are too simple. For example, sequences are the ones that we're going to be using throughout. Lists are so generic that they don't need the entries to have any special format. They don't need to be compatible with one another. But if you read about sequences, they're like lists in that they're a sequence of objects, but they're similar to one another. They need to be similar to one another. Well, okay, so one problem is that sequences are very powerful. You can operate on them quickly. Lists will be difficult to work with. So here we have to have our first taste of conversion to a different kind of object. Let's call it C. Now this is the set constructor operation. I will just write, so it's perhaps unpleasant to read, but very simple. So I'm saying run through elements in B. So I'm referring to the elements in B as BB. And then here there's some evaluation operation. Well, nothing is, I'm just saying don't do anything, just plug in BB. And then the difference here is that I don't have stars around my brackets. This will be a sequence. And now let's print C. let's try a function again. So now we printed C. This is going to be a sequence. We can see, for example, the sec enum refers to a sequence, an enumerated type list. Now the reason we went to the trouble of reading about lists and then learning a little bit about sequences is the following. I can write ampersand plus C to add all elements in C. And that's very convenient, because after I write A plus ampersand A plus C, so this should be seen as the sum of elements in C, and then to that sum I'm just adding A. I've really added all the inputs that have been given to me. Let's clean this junk and then we can copy paste. Okay, so add all. Now we really did add the given numbers. Now if you want to find more about this ampersand, because it's an extremely useful operator, you can go and write the question mark ampersand and therefore ask about the ampersand. Now as usual, when in doubt, you can just choose the first operation, but also you can read a little bit what this is saying. So there's a sequence here, and we're operating on sequences, so it seems reasonable that the first option really will help us. And now this is a very good explanation here. It says that I can apply an associative operator to a sequence so that this binary operator becomes multiple operator and takes all these entries. For example, plus is possible, multiplication or star is possible. For booleans you can use and, or for sets and sequences you can use join, meet, concatenate, cat for strings. So that's very helpful. And let me show you what cat does. It just joins two strings. Very good. One last thing. So now you can put a lot of inputs to this function, but here I have 255 ones. Now we can check that there are 255 ones. As you see, we get 255 here. Remember, this was a comment, it doesn't do anything. But now if I add one more one, then this breaks. So you can see that the limit is 255, one less than 256. Since you have to type in these inputs manually, it's very unlikely that you will break this limit unless you're explicitly trying to. There are three ways to create a function. The first one I've already introduced. You write function, the function name, and then so on. But you can also write a function without declaring its name. So you could, for example, write function a, return a, end function. Of course, this is not very useful as it is. What it does right now is that it creates a function that is the identity function. It takes in a, returns a, and there has been no assignment of this function to an identifier, to a name. So what happens is, if you write it as it is here, you will get an extra line that we did not see before. My function declaration really ended here, and this is the output. So it outputs my function without the intermediate statements. What I can do is that instead identify this output and give it a name. For example, my ID, my identity function. If I copy paste, so my ID now is the identity function. So this version can be useful. The most striking difference is that this function, upon creation, so here it does not know its name. Therefore, it cannot reference itself through the use of a name. There is a way for a function to reference to itself without a name, and we will come to it later, but that's probably the most important difference. And then there's a shorthand version for creating a function, just like we've done before. Let's do something a little bit more interesting. So again, an add addition functions. So I'm going to create a function and assign it to the name myAdd. You can write func, again shorthand. I take two inputs, a, b. All the spaces are unnecessary, just for our visual aid. So this says so far that the function takes two inputs. I put this vertical line, pipe, and then I'm going to add them, and then end of function, and then end of command. Let's see what this does. Again, it's just an addition function. What's new here is that with this addition function, You cannot do intermediate operations. This is really for shorthand functions. For example, if I were to say, let C be AB, and then I want to return the value of C, this would crash. So it's not allowed to do interesting operations inside. You must have a single statement, and this statement is returned. You also don't have to write return here. This version of function declaration can be useful in two different ways. One of them is, well, you just don't want to type in long function declarations for simple operations, but also you can create them during the creation of a sequence. For example, remember I can do something like this. So this is just a sequence of numbers from 1 through 5. This is, of course, quite useless. I could have just written this, which achieves the same effect in practice. But here's what I'm going to do now. Instead of n, I'm going to create a function a, so that this will be a function with a single input. I'll call it a, and I will shift it by n. So this is a sequence of functions. Each of them shifts the entry by a certain integer. So I give the sequence a name called shifts. Now what happens is that if I write shifts1, it says, well, this is a function, and it's a function with a single input. The input is called a, but it omits the statement. Okay, we can find out which function it is by giving it an input. So I now call my function, the first function, or the function at index 1, and I plug in 0. So evaluated at 0, it will return n. So n should be 1. So we've learned a couple of things here. One of them is that sequences are indexed the way a human would index them, not like a machine would index them. So the sequences start at number 1, not at number 0, like most programming languages. So far, we've been playing around with the basic syntax of function creation. We've learned, for example, that a function can be created that takes no input, 1 input, 2 input, or 3, or whatever. And of course, we learned about this syntax where you can have multiple inputs and an arbitrary number of inputs. Well, it should be at least more than the number of names here. And we learned about an object type called lists, about sequences, how to convert a list into a sequence, at least one way. We've learned about this ampersand operation. This was very important, very useful. We've learned how to break a function with a supposedly arbitrary number of inputs, not that it happens in practice. We've learned about different ways of creating functions, for example, without a name, the shorthand version, and very simple use of how to benefit from the shorthand, for example. We're now going to write a function that computes the Fibonacci sequence. That's at least a little bit more fun, and we will really learn about recursions.